Good afternoon, everyone. So I will be presenting my work MESSI, behavioral testing of the BGP implementations, and it is my joint work with my collaborators at UCLA and Microsoft. So as we know that BGP is the backbone of modern internet routing, and it is connecting different autonomous systems, and it is ubiquitous, used by different ISPs, data centers, enterprises everywhere. But it has also the unfortunate property of large blast radius. That means if something goes wrong with BGP, then it has a global effect. And we have seen this previously, different clouds like Google, Microsoft, YouTube, Facebook, they are going down. So there is a need for BGP testing. Now, most of the previous works on BGP testing has been done on identifying the BGP configuration bugs. So we have seen a lot of them. But according to some study, nearly 36% of different customer impacting bugs, they are arising from the BGP implementations. But significantly less work has been done on testing the BGP protocol implementations, automatically finding test cases for them. So in this work, our goal is to automatically generate test cases for BGP protocol implementations to find the behavioral bugs. So this is how a test case looks like. It has, it is a triplet. It contains three things: the configurations, which is the route map, the state, and the route. So route is basically the route advertisement, which is a control message announcing the availability of a path. And the configuration is the route map, which is modifying or filters a route before installing it into the RIB and passing it on to the other routers. And then there is state. This is the feature of BGP. It is a stateful protocol. According to the state, the router decides what to do with the route announcement received. So the key challenge in automatically generating BGP tests is to generate this triplet. This joint generation of this triplet is the key challenge. Now we discuss why the existing approaches like fuzz testing and symbolic execution, what is their limitation in BGP test generation. So fuzz testing basically randomly generates test cases, but it is unlikely to find the bugs which require some particular combinations of these three things: configuration, state, and the route advertisement. So therefore, fuzz testing can give us limited coverage on the behavioral bugs. Similarly, like symbolic execution can generate interesting combinations, but it suffers from the path explosion problem because the actual implementations, they do not only have the behavioral code, but they also have some low level optimizations. So therefore, the coverage is an issue, and also in some cases we do not have the implementation available because some of them are closed source. So in this talk, we discuss our tool and our approach MESSI, modular exploration of state and structure inclusively. So this is the first automated approach and tool MESSI to test the BGP black box implementations and to find the RFC compliance. So here there are three key ideas. One is how we use the modular exploration, and also how we deal with the BGP specific challenges like state and structure. So here are some of the key results that we found using our tool MESSI. It generated almost 150,000 test cases. We found 22 bugs across 6 popular BGP implementations like FRR, Quagga, Bird, GoBGP, Batfish, and First Plane. So some of them are serving as the basis for different other BGP implementations, just like FRR serves as the basis for Microsoft's popular BGP implementation Sonic. So we found bugs in almost every aspect of BGP, like the prefix list, regular expressions, communities, AS path, MED, and incremental updates of BGP. And 8 of the bugs are already fixed and acknowledged by the developers. So now we already saw that what are the limitations of existing approaches. So now we discuss our approach, which is model based testing. So in model based testing, we use the BGP RFCs as our specification, and then we create an executable model of BGP, and then we do a symbolic execution on that executable model. Now this solves the previous problems because it can now generate the test cases which can capture complex behaviors of this configuration, state, and the route advertisement. So this joint generation of the triplet is possible, and also it is not suffering from the path explosion problem because we are only modeling the behavioral code. We are not testing we are not doing symbolic execution on all the low level optimizations which the actual implementations might have. And it also can give some coverage guarantees on the bounded size of the inputs, just like we can bound the number of stanzas in the route map, and also we can specify some ranges in the route attributes. So by that we are also gaining the coverage guarantees. Now what are the key challenges in this BGP test generation? So this model based testing approach was previously used in a work called Scale for DNS testing bugs in the DNS name servers. But what are the BGP specific challenges? So the first is BGP has a lot of components like filtering, decision process and aggregation, and they are interacting with one another. So if we build a monolithic model, that would also suffer from the path explosion similar to the symbolic execution. So we cannot build a monolithic model. Now the second problem is BGP is stateful. In case of DNS name servers, we only had two inputs, the query and the zone file. The zone file serves as a configuration and the query is the message. But here in case of BGP, we have another input variable which is the state. So that increases the input space, and again we get some coverage issue. Also BGP has these complex configurations called the route maps, which are like small little programs which adds to the complexity of the model. And also we can have regular expressions as communities or AS path in the route map, which is beyond the capacity of current solvers. We cannot handle regular expressions symbolically. So these are the BGP specific challenges we are going to deal with. So now we discuss that how we deal with each of these challenges. So to deal with the protocol complexity, we use modularity. So from the BGP RFC, which is the specification, instead of building a monolithic model, we build models for each of the BGP features like decision process, route filtering, aggregation, and dynamics means the incremental updates of BGP. So by building these separate models, and then we run symbolic execution on each of them separately, and we generate the test cases. So here the benefit we are getting is quite simple, that suppose decision and filtering process, they are intertwined. When a route advertisement is coming, it is first going through the route filtering process, and then the filtered routes, among the filtered routes, we run the BGP path selection algorithm, which is the decision process. So if we had built this in a monolithic way, suppose the filtering is having m paths and the decision n paths, then we had total m cross n paths in the model. But if we break that down, then we have m plus n paths. So that allows us to dive deep into each of these modules and test them exhaustively. So this is how by modularity we are solving the complexity problem. And we also found that this modularity can help us to overcome the state problem as well. Like in case of route filtering, we do not need any state. It only depends on an incoming route, the attributes of the incoming route, and the configuration, which is the route map. So no state is required in route filtering. And in decision process, we see there is only one state required, that is the best path that is already saved at the router. And we do not need any configuration for the decision process. So this is how each of these models only needs only whatever symbolic states are required minimum. It's only modeling the minimum requirements. So this is how we solving the state problems, and the state space is not blown up. Now we talk about another kind of statefulness in BGP, which is arising from the BGP dynamics or the incremental updates of BGP. So what is the motivation behind this kind of testing? And this is one of our contributions, that in the previous work we have never seen this kind of testing before. So while observing the bug databases, we found that many of these bugs are coming from the optimizations used in the implementations for incremental updates. So suppose I have a route map, I make some local changes to the route map, and the router is not behaving in an expected way once the change is made. So how to capture these kind of bugs using our approach, which is model based testing. So let's discuss that. Just to remind you, this is the normal route filtering where we have a symbolic route map, a symbolic route, and the route filtering model gives us accept or deny. So if we run the symbolic execution, it will give us these symbolic inputs. Now how the dynamic route filtering differs from the normal route filtering? So in case of dynamic route filtering, we have an initial route map which is symbolic, then we have another route map which is updated, and a route advertisement. So the symbolic execution model generates 3 inputs instead of 2, and 2 of them are the initial route map and the updated route map. And the dynamic route filtering model returns true if the decision differs. Decision differs means, suppose this is my route advertisement. Initially this route was allowed, so after the update the route advertisement should not be allowed, then it returns true. We are doing this because unless by the change some decision is altered, we cannot really know whether this is, we cannot really observe the change. So for testing the incremental updates, we have to make a precondition that the initial route map and the updated route map should have different decisions. So now this initial and the updated route map can differ in many ways. So to restrict the state space, we are keeping the Hamming distance between these 2 route maps very small, like 1 or 2 local changes. So otherwise the state space will blow up, and also it is motivated by the fact that the operators, when they locally change the route map, they do not entirely change the route map but only a few features in that. So this is how we test the BGP dynamics, which is another kind of statefulness. So we have already solved 2 problems. One is coming from the complexity of the model and the statefulness. Now we deal with the third kind of problem, which is regular expressions. So this is how our test case looks like. It has a configuration, state, and the route advertisement. The configuration is basically the route map, and the route map can have regular expressions in community and AS path. Now if we symbolically generate this route map, there is a problem. Then we have to model the regular expression constants within our symbolic model, and which is beyond the capacity of current solvers, because the regular expression is having non-regular grammar. And in general the solvers are quite slow with the theory of strings, and therefore regular expression is a difficult task to model symbolically. So that means we have to deal with the regular expressions externally, and we have to use a fixed set of regular expression that the model can use for generating test cases. Now how can we generate, how can we give some coverage guarantees on that fixed set of regular expressions? So that is how, for solving that problem, we have this regular expression and testing framework. So here we use a hybrid approach, which is coming from enumeration, fuzzing, and graph traversal. So first we enumerate regular expression shapes up to a certain size, and the regular expression shapes look like something like this. So x is a placeholder here, and it is generating a regular expression shape up to a certain size. In our case we generated regular expressions up to size 3. Then we populate the regular expression templates with some random regular expressions, and we get some concrete regular expression which will go into the route map. Now that is not sufficient, we have to also generate some positive and negative strings which match and do not match with this regular expression, and that goes into the route as a community or AS path. So for that we generate some positive and negative examples by converting this concrete regular expression into a DFA, and on that DFA we do some graph traversals using depth first search, and we make sure that each of the node and each of this edge is present in at least one of the examples. So that is how we give some node and edge coverage guarantees by doing DFS on the regular expression DFA. And then we generate the positive and negative examples. So we have the concrete regular expressions which is coming from enumeration followed by fuzzing, and then we have the graph traversal to generate the positive and negative example. With this fixed set of regular expression and the examples, we can give it to the symbolic module, and the symbolic module can use them to generate test cases. So here we have 2 coverage guarantees. One is coming from the enumeration, where we exhaustively generate the regular expression shapes up to a certain length, and also another coverage guarantee is coming from this node and edge coverage algorithms from the graph traversal in terms of the positive and negative examples. So in short, these are the results. We have already discussed about them. And now I will go through some of the example bugs which will show the subtlety and how it is non-trivial to find these bugs. So our tool MESSI generated a route map which looks like this, and also generated a route advertisement. And if you see the route map, it should allow all prefixes with mask length 10, and the generated route is also having the mask length 10. So it should be accepted to the RIB, but GoBGP is not accepting the route. So there is a bug which is arising from dealing with the 0000 prefix with a single mask length. So we can see how some particular combination of this configuration and the route advertisement is causing these bugs, which are non-trivial to find. Another bug from FRR which shows the use of incremental, why we are testing the incremental updates. So our tool MESSI generated a route map and also a route, and according to this route map, any prefixes should be accepted. So this prefix gets installed in the RIB. Now if we change the prefix from prefix any to some particular prefix, now this particular route advertisement should not be accepted, but the routing information base is not updated. So we can see that this is a non-trivial bug coming from the incremental updates, and the reason behind this was there was some underlying flag which was enabled when the route map was given prefix any, and even after the update that flag was not turned off. So therefore it is still allowing all the different prefixes. So we can see here how it is non-trivial. If we restart the router and give this configuration, it will work perfectly, but only when we transition from prefix any to this prefix, then the bug is coming. So it shows the stateful nature of BGP. So these are our contributions. Our tool MESSI is the first automated approach to test RFC violations in black box BGP implementations. We have used the modular exploration to deal with the protocol complexity. Also we have efficient enumerative testing of the regular expressions which cannot be handled by the symbolic solvers, and also we have this testing framework for BGP dynamics to test the incremental updates of BGP. Thank you very much for your time, and I am ready to take any questions.